Page 7 of normal distribution, number 5 here at the top. These are from the new curriculum books. So slightly different twists on the same old problems. First of all, the way they present the data here is something that they're going to use in other new units also. They define the normal distribution, which is defined, remember, by two characteristics, mean and standard deviation. So like the first number they give here is the mean, and notice that the standard deviation is squared. They give the standard deviation here, and they put a 2 above it because it's a squared value. The reason why is because in statistics, a lot of times they talk about variance, which is standard deviation squared. So 3.1 squared which is about 9 would be the variance, and 3.1 would be the standard deviation. They want to use the notation, but they want to give you a hint that actually the standard deviation is 3.1 and not 3.1 squared, so they leave it unsimplified there. What does the n mean? The n means that it's a normal distribution. So here they can use different letters to signify what kind of distribution it is. So remember, normal distribution looks like a bell, and so this is a normal distribution, but there might be other distributions. So that's why they have the letter here. T is just a random variable. So they're saying, oh, the random variable t, this number is going to be a randomly chosen number in a normal distribution with the mean of 17.1 and a standard deviation of 3.1 is all they're saying. And then this little tilde here is to say, oh, the t is distributed normally in this configuration. Okay? So, all right. So it says to estimate these probabilities without using technology. So let's try to do that. So first thing we're going to do is, as usual, and since we're not going to use technology, I'm just going to cover up the calculator for a while. So I'm going to draw a picture like we normally do. And in the middle, I'm going to put 17.1 because that's the mean. And then if I draw standard deviation lines, they're going to be separated by 3.1. So the next line is going to be, let's see, 3.1 would be 20.2. And the next line would be 23.3, right? And then 17.1 minus 3.1 is 14.0, and the next one over would be 10.9. Okay? All right. So it says to estimate these probabilities without using technology. First it says, what's the probability that t is less than 17.1? Well, remember, that would be this region here, okay, which would be 50%, okay? And that wouldn't even be much of a... that wouldn't even be much of an estimate. It would actually be the exact answer, right? So this would be 50%, 0.5. B would be, what is the probability that t is less than 14? So that would be this region here, okay? Makes it easier to erase if I don't put it right on top of it. Okay, so that would be this region here is, remember, 13.5, and this one here is 2, and this one here is 0.5. So actually, if you add these up together, it makes 16%, which makes sense because the middle partitions are worth 34, right? So this would be 16%, or 0.16. C, probability that t is greater than 20.2, that would be this region here, right? And that would be also 0.16. Oops. 0.16. Okay, not right now. Gosh, darn it. Okay, D. Probability that t is between 14 and 23.3. So 14 is here, and 23.3 is here. That looks like it would be 34 plus 34, which is 68, plus 13.5. So 68 plus 13.5, that would be 78 plus 3.5, which would be 81.5. They told me not to use technology, so I'm trying to do everything without a calculator. Okay, and finally, this last one is a challenge because you... may remember that in the probability unit we used the vertical line to signify such that, given that, which is conditional probability, right? So basically what they're saying is, given that this red event happened, what is the probability that the blue event happens? And the way you do these problems is you make a fraction. So this probability here is, you could write t is less than 23.3. Given that t is greater than 20.2, it's equal to the probability that both happen divided by the probability that the red event happens, okay? Maybe I should have color-coded this blue, right? I'm going to put t is less than 23.3, so you know that's the blue event. Okay? So one thing that that you can see is the probability that 20.2, I'm going to use the yellow, or I'm going to use red to signify. Where is the probability that t is greater than 20.2? That would be here, right? Where is the probability that t is less than 23.3? Less than 23.3, that would be here. So when I want the probability of both happening, which would be the red and the blue, that would basically be this one section here. So what's the probability of that happening? Well, according to 689599, this would be 13.5, right? So I'm going to put 13.5% is going to be, and I'm going to write it in decimals here. So the top is going to be 0.135 because that's the part where both happened. And then the probability that t is greater than 20.2 is the red part, which is 13.5 plus 2 plus 0.5. It's 16%. So the red part is 16%. I'm going to put in decimal also. Okay, now I cannot do this without the calculator. That would take forever. I would have to do long division. So 0.135 divided by 0.16 is equal to 0.84375. Okay, since that's an exact answer with 5 significant figures, no use in rounding it, it's fine, right? Okay, so that is the probability that t is less than 23.3, given that t is greater than 20.2. All right. All right, let's go to the next one. So this one is very similar. What is the mean in this case? Well, let's make sure first it's n, so that means normally distributed. So that means we can use the normal distribution rules like 68, 95, 99 and norm CDF, right? 4.03 is the mean and 0.7 is the sigma, and then the square is squared. 0.7 squared is the variance, 0.49 is the variance, but 0.7 is the sigma, or the standard deviation. And we only want the standard deviation. So if they ever put something here that's not squared, that is going to complicate your life, and hopefully they'll never do that. Okay, find these probabilities with technology. Okay, so the probability, okay, let's first of all, we'll draw our picture like we usually do, right? So in the middle, we're going to put the mean, which is 4.03, and then the standard deviation is 0.7, so we'll put 4.73 here. We'll put 5.43 here. We're going to put 3.33 here. We're going to put 2.63 here. Okay? So this problem says to use technology, so we open up the calculator here, and we're going to use the calculator to calculate these values with second distribution norm CDF, right? So the first thing says, what is the probability that Q is less than 4? So we're going to do norm CDF, because in this case they're giving us numbers on the x-axis, and we want to find the area or the probability. Of course, this area that we're going to look at is less than 4, so it's slightly to the left of 4.03. Looks like it's slightly less than 50%. Let's see how much exactly it is. The left boundary is negative infinity. The right boundary is 4. The mean is 4.03. The standard deviation is 0.7 because it says 0.7 squared. And the answer is 0.483. And so I'm going to put 0.483 because that's 3 significant figures. I'm going to erase my picture there. And then now I'm going to look at Q is greater than 5. Q is greater than 5. That would be more toward here, right? So that looks like it would be maybe like 10% or something. Let's see how much that is. Second distribution. It's always good to look at your picture and make a guess, because then when you get your answer and it's like totally different, then you're like, okay, did I guess wrong or did I make a mistake with the calculator? So now I'm going to go from 5 to positive infinity, which would be 1 EE99. And the mean and the standard deviation is the same. And I'm going to paste that. And it gives me 0.0829. So I was pretty close. I said 10%, right? 0.0829. I did C instead of B. I want to do B. Okay, so now I'm going to do greater than 3.4. Okay, it's not greater than 3.4. It's less than 3.4. So let's do less than 3.4. So the right boundary is 3.4, and the left boundary is going to be negative 1E99. So let's do that. Norm CDF. And it'd be negative 1E99. And then the right boundary is going to be 3.4. And then the mean and the standard deviation are the same. And I'm going to paste that. And I get 0.1184. By the way, if you were going to draw this, it would be about like that. Okay, slightly more than 16%, right? Oops. Okay, and D, we want to know the probability that it's between 3.5 and 4.5. So this is the easiest kind because you don't need to figure out if one side's negative infinity or not. They give you the left boundary and they give you the right boundary. So this is 3.5 is the left boundary and the right boundary is 4.5. Notice that here it has less than or equal to and this has less than. Does that matter? No. In normal distribution, it doesn't matter because the area directly above the number 3.5, 4.5 is infinitesimally small. So it doesn't matter if you include it or not. It's kind of a weird thing, which kind of has some calculus concepts on it that we're going to talk about when we do normal distribution. Okay? So this answer is going to be 0.525. Last of all, again with the conditional probability. So remember, what we're going to do is we're going to treat this as the numerator and this is the denominator. So first of all, we're going to have the probability that Q is less than 4.9 given that Q is greater than 2.9. What we're going to do is we're going to say, okay, what does greater than 2.9 mean? That would be this here, this area here. And then what does less than 4.9 mean? That would be this area here. And the overlapping area where both happen, that goes in the numerator. So we want the probability of both divided by the probability of the red. So we're going to put the part that's both would be, what number is that there? So this is this number is 2.9, right? And what number is this here? It is 4.9. Okay, so the probability of both happening would be between 2.9 and 4.9. So let's figure out what that is. Second distribution, normal CDF, probability that it's between 2.9 and 4.9 because that's both events happening. And the answer is 0.8398. If I round that to 3 significant figures, it would be 0.840. That would be the top. Oops, since it's the top, I'm going to write it in blue. And then the bottom is the probability of red. The probability of red is that Q is greater than 2.9. Okay, so greater than 2.9 would be I would put 2.9 for the left, and I would put 1E99 for the upper. And the answer is 0.947 is the bottom. And then the proportion divided out would be 0.84 divided by 0.947. So the answer would be 0.887. Okay? All right. Then let's go down to the next problem. Okay, so these are talking about, it's mixing some concepts we had in statistics with some concepts now. Remember box and whiskers plots. So now what we're going to do is we're going to relate box and whiskers plots to the normal distribution. Okay, so remember, when you have these tall bars in normal distribution, what that means is you have a certain number of occurrences. So let's do this. I'm gonna like look at each one of these, and I'm gonna try to like figure out how this would look as a box and whiskers plot by deciding where do I have 25% of the population. Okay, so for example, for this one here, I can see that the middle of the population is there, right? Because it's symmetrical. Now, where is 25% of the population? Well, it looks like that most of the population is over here. So if I wanted to circle 25% of the population starting with 0, it would be like this much, right? I didn't want to include too much of that tall bar because some of the tall bar needs to go with the next part, okay? So maybe this would be 25% of the people if I count up all these little blocks, and this would be 25% of people if I count up all these blocks. Do you notice how I put some of the big block to the left and I put some of it to the right? Same thing with this one. I would need to put just a little bit of the big block here, but like most of it maybe here. Okay, so do you see how like these two pieces are like wider than the other two pieces? Okay, let's do the same thing with B. For B, I would say that the middle is a little bit to the left, right? So maybe like it's here, okay, because there's a lot of empty ones here. Then I'm going to divide, let's see, if I was going to divide this left part into half, I would say that like this would be half, and then this would be the other half, right? And then if I were to divide the right half into halves, and when I divide a half into a half, I get 1/4, right? So I would say that like this would be like one part, and then maybe this would be like a skinny part, okay? So like when you have a lot of people represented by this tall bar, then you don't have as wide of a region because it doesn't take as much width to include that many people, okay? Now here, the middle is obviously right there. Now, most of the people are crammed in the middle, so if I took that section, that's already 1/4 of the people, and then this section would be the rest of the 1/4. So you can see that like the regions I'm making are like wider when there's not too many people and when the people are less dense. Here's the middle of this one. It's symmetrical. Now on this one, if I want to include 1/4 of the people, I need to like go a little bit further out, right? Because there's hardly any people here. And then the last bar has a ton of people, so the horizontal region, which includes 25% of the people, doesn't need to be very wide. And this is a very interesting distribution. So like the middle of this distribution, the middle person of the distribution is over here, right? And then the number of people that are in this part are much fewer than this part, so I need to include a wider area to include the same 25%, and then same as I get over here. So like this, the smallest region would be the left side, okay? Now what I'm going to do is I'm going to just like look for the histograms which have this shape. This shape, this shape, this shape, this shape, and last of all, this shape. Okay, so doesn't this one look like 2? Let's see. What about D? D kind of looks like this. D. 1. This one, which is kind of all built up on the left side, that kind of looks like this one, right? So that would be B. 4. And then this one that's all skinny in the middle looks like C. And then E, which looks progressively skinnier as you go to the left, that looks like 3. Okay? Make sense? All right, those are kind of tough. Identify the one histogram of the data set that follows the normal distribution. Okay, well, looking at the original pictures, I can see that this one looks like normal distribution because it's symmetrical and it's got a big bump in the middle, right? So I would say the answer is 5. Oops. 5. State with a reason which statement is true. P, a data set whose histogram is symmetric can be represented by a symmetric box and whisker diagram. That's true, right? Let's erase these for a second so we can remember what the diagrams look like. The ones that are symmetric are number 2, or letter A, and letter C, and letter D. So A, C, D are symmetric. Are 1, 2, 5 also symmetric? 1, 2, 5. That's true. And the reason why is because if the histogram has people evenly balanced out, okay, so will the box and whiskers. So P is true. What about Q? A data set that follows the normal distribution must have a symmetric box and whisker diagram. A normal distribution must have, yeah, because normal distribution is symmetric. So if the normal distribution is symmetric, then the box and whisker also has to be symmetric. A data set with a symmetric box and whisker diagram must be normally distributed. Okay, so if you have a box and whisker diagram that's symmetric, such as D, is that normally distribution? Or 1, let's see if D is normally distributed. No, it's not. It's like got a big valley in the middle, right? Normal distribution has a bump in the middle. It's bell-shaped. So, no, it's not true that just because a box and whisker diagram is symmetric that it corresponds to a distribution that is normally distributed. Okay? Even though normal distributions are symmetric, the all symmetric distributions are not normally distributed, right?